Okay.
So hi everyone, my name is Bob Monahan. I'm with the advising team here for ECEE students. Thanks for being here. This is the pathway presentation of two of our academic areas. One is physical electronics and photonics, and the other is the power area. And we're going to get started with the physical electronics and photonics, or PEP area, with Professor Trevor Thornton. So thanks for being here, Trevor, and please take it away.
Well, very good. I'll start sharing my screen now. So can you tell me, do you see I'm going to put it on full screen. So let me know, do you see my full screen page or my notes page?
Nope, I see your full screen and that beautiful Waymo.
Okay, very good. Well, that's a great place to start because I think these self-driving cars exemplify where we are with physical electronics and photonics. And that's because you can see underneath, I guess most of you are in the Tempe area, right? If you walk around Tempe, even on the ASU campus, you'll see these self-driving cars, people dropping off and being picked up without anybody actually driving the car. And the reason it can do that is because of this very advanced semiconductor technology. So, of course, we know about computers. Oh, I want to just very quickly annotate. Let's see, can I use my laser pointer? So no, that's bear with me for a minute. They've changed, there it is, spotlight. Maybe I'll do that. Okay, so there's my laser pointer. Hopefully you can see that. So computers, of course, of the compute technology has increased significantly, and we'll talk about Moore's law and all that good stuff. But then also, we try not to stovepipe ourselves in engineering, right? We don't want to say I do computers and I do power and I do radar, because they're all entwined. And so this system runs, it's fully electric, right? It has voltage levels from 480 volts down to like less than 1 volt for the microprocessor. So very advanced power conversion technologies. Radar, look, it has all these sensors on the top, this LiDAR, the RF communication allows it to interface with the web, with the cloud. And then the feedback control and signal processing that's required to do that. It's kind of phenomenal. Hard to imagine that these are on our streets. Even 10 years ago, that would have been very unlikely. And the reason we've done all this is because we've advanced so much in the last 60, 70 years. And so around the Second World War, vacuum tubes were used to develop the first computers. And then the folks at Bell Labs developed the first transistor. This is a photograph of something that they have in the Smithsonian Museums in Washington. So this is a bipolar junction transistor made from bits of germanium essentially glued together with solder. Amazing. So we've gone all the way from that to, I think the latest thing are these NVIDIA AI chips. I mean, it's astonishing. I remember getting my first NVIDIA card for a video card for my computer, and it was a pretty niche thing in those days. And of course, now they've cornered the market in these AI chips. And at one point, a few weeks ago, they were the most highly valued company on the planet. So astonishing. We all seen what that AI can do. Self-driving cars, we talked about that. Solar power, right? Just in the last 10 years, solar power has become as cost-effective as carbon-based sources. So real drops in prices. And then the technology has merged from being just sort of analog to digital to now fully RF. We can build 100 gigahertz plus several hundred gigahertz RF integrated circuits that we use in our very advanced communication systems. So it really combines everything that I talked about, knowledge of semiconductors, knowledge of electromagnetics, knowledge of signal processing. So, power, everything is required there. And of course, it's all made possible by this Moore's law. And the number of transistors on a chip doubles approximately 18 months, and that's been true for the last 60 plus years. They're always predicting the demise of Moore's law, and then very clever engineers figure out ways to get around those problems. So this is the piece I wanted to emphasize here. What do we need to know? Well, we have various courses that really essentially focus on what we could call device physics. How does current flow in a semiconductor, a metal, or not flow in an insulator? Then how do you take those devices and how do you implement them in practical circuits that do the functions that we need? And that's all the way from fairly low scale integration. So RF integrated circuit design may just have a few hundred active components, all the way up to these NVIDIA chips that have, tens of billions of transistors and other components on a chip about a square centimeter. How do you build those things, right? We're very lucky here at ASU. We have a clean room on campus that we use to teach students the fabrication techniques for manufacturing these semiconductors. And then modeling is extremely important. And by that, I mean the TCAD, so technical computer aided design. These are sophisticated software tools that take the fundamental equations from the device physics and then implement them so that we can do real physics-based simulations of how these devices and circuits work. And then finally, the measurements. If you have circuits that are consuming picowatts of power, nanoamps, microvolts, all the way up to kilowatts and even megawatts of power in some extreme cases. How do you measure those systems? How do you characterize those? So you need a pretty diverse skill set to be able to work in this physical electronics and photonics. And that's what we try to introduce you to. These are the 400 level classes that we offer. Now, all right, just between us and don't tell the dean, all my degrees are in physics. So back in the day when I was a student, similar in age to most of you, we were interested in quantum mechanics and applying quantum mechanics to current transport in semiconductors. And so roll on 40 years, what was applied physics is now everyday engineering. And so quantum mechanics is important for engineers. It defines how the lasers and LEDs work. It defines how the current flows in these highly scaled silicon CMOS transistors. So EEE 434, a generation or two ago, it would have been unusual to have a quantum mechanics class in an engineering program, but now we have a fairly introductory quantum mechanics class, EEE 434. And then the class I've been teaching recently, I mentioned this earlier, 435, fundamentals of CMOS and MEMS. I'm sure you know, but CMOS is complementary metal oxide semiconductors, and MEMS are micro electromechanical systems. When you rotate your cell phone, the orientation of the display changes, and that's because there's a mechanical accelerometer built onto the silicon chip, and that's commonly referred to as a MEMS chip. So during this class, we address the fundamentals of semiconductor manufacturing, and we take the on-campus students into our clean room for labs that demonstrate the basic steps involved in manufacturing a CMOS or MEMS integrated circuit. Okay, EEE 436. This is the sort of fundamental class that underpins how semiconductor diodes and transistors, especially MOSFETs, work. So 352, properties of materials, is the sort of a prerequisite for this class. And in 352, we basically explain how the electrical properties of metals, insulators, and semiconductors. And we end up explaining how a PN junction diode works. Then in 436, we build on that. We go a little bit further into the operation of a PN junction diode. And then we start talking about transistors, and in particular, how a MOSFET operates. And so if you're going to understand how your circuit works, you need to understand the fundamentals of the actual devices. And then the sort of sister course to 436, 437 is optoelectronics. So while 436 focuses on electrical devices, diodes and transistors, the 437 class optoelectronics focuses on optical devices. So light emitting diodes, photodetectors, lasers, etc. Then 439 is semiconductor facilities and clean room practices. And I think we may have changed the name of this recently to semiconductor manufacturing, but that was really just, that may not take place until next semester. But this is really, how do you design and operate the clean rooms that we need to be able to build these kinds of highly scaled semiconductor chips. And being here in the Valley, I'll touch on this later, we have all these semiconductor manufacturing companies. And so having some understanding of how those facilities operates can be very valuable. And then, of course, here in the desert, we have an abundance of sunshine. So it's a very obvious place to do photovoltaic energy conversion. And we have strong faculty programs researching next generation solar power technologies. And so our 400 level class introducing many of those ideas is 465 photovoltaic energy conversion, so PV. And I mentioned this, we have a lot of research projects that are very well funded, very well thought of by the different funding agencies and companies that sponsor them. And that's very useful, I think, for the classes because it brings the latest research and development ideas into the classroom. And so you can get exposed to some of the very latest ideas. So a colleague of ours a few years ago demonstrated the first white laser. So this is kind of contrary to what you expect, right? Lasers were invented because they emit light at just one very precise frequency, one very precise wavelength, which is very valuable if you're talking about communication systems. But we see things with the white light spectrum. And so if you're going to make a high brightness, high contrast television, you'd like to be able to drive each of those pixels, not just with an LED or an LCD device. You'd actually like to use a laser. And so a colleague of ours figured out how to combine both a red, green, and a blue laser onto the same substrate so that when it lasers, it actually looks white. And so that's causing a lot of interest for next generation televisions. I mentioned the solar research. I'd also like to point out wide bandgap semiconductors. So traditional semiconductors like silicon, and if you remember back to the 352 class, they have a band gap between the conduction band and the valence band of about 1.1, 1.2 volts. And that's been very useful for all our commercial technologies. But for many applications, we'd like to have devices that have a larger band gap than that. So new foundry services such as gallium nitride are now available. And again, in the Valley, we have companies like NXP Semiconductor building next generation gallium nitride chips that go in everywhere from, I don't know if you've got one of the high-speed phone chargers first introduced by Apple. Those use gallium nitride, and they allowed you to charge your cell phone much faster than the previous ones, all the way up to silicon carbide. If you have a Tesla, all the power electronics in the Tesla are controlled by silicon carbide transistors. And then my personal interest recently is in diamond electronics. Diamond has the highest thermal conductivity of any material we know, and often the systems applications of these things are limited by how much power they can dissipate. And so if you can use diamond to efficiently get rid of all that extra heat, you can imagine applications that you can't do with any other technology. Put a transistor chip into the exhaust plume of a jet engine, for example. And then this is all tied together with our nanofab facility. This is our photolithography engineer, Carrie Sinclair, working on one of our contact aligners. And so these are one of the tools that the students are using in the clean room when they take my EEE 435 class. So a lot of work going on in industry. So what do semiconductor engineers and scientists do in industry? Well, I tell this to all my students. We're talking this discussion is about physical electronics and photonics, PEP. But if you're interested in PEP, then you should definitely broaden your experience by looking at circuit design, right? Why do we make these transistors? It's not because not very many of them are used individually. They're all put into circuits. So understanding how you design, layout, and test circuits for manufacturing is very key. I mentioned simulation and modeling, those TCAD software tools that allow you to simulate a circuit before you actually build it. This is one of the points that Intel often makes, that they are very successful in the first pass design success of a new chip. So they will simulate the heck out of a chip, and they will only fabricate it when they're absolutely convinced that everything is taken care of, so that when that chip is fabricated, it will work first time. And if you think that a mask set for state-of-the-art chipset can cost approaching $100 million, you don't want to be redesigning that mask set because you made a mistake in one part of the initial design. So simulation and modeling is very important. Fabrication, these new semiconductor manufacturing facilities that I'll talk about cost $20 billion to build one. And so, clearly being able to fabricate circuits and components in those facilities is a major challenge and a major investment by industry. And then there's measurement and characterization. There's an industry that hundreds of companies that the public has never heard of that make a very good business designing and manufacturing tools that are used to measure and characterize semiconductors. And then finally, sales and marketing. You need to be able to explain to your customers what your technology can do that your competitors can't. And so having a good understanding of how your systems, services can help your customers is vital. And that's a very unique kind of skill set. So I think this is pretty obvious to some people. I want to just draw your attention to this picture in the middle. This is the extreme ultraviolet lithography tool manufactured by ASML. This is a very interesting piece of equipment. The New York Times, in an article a year or two ago, called it the most complicated machine ever made. It's the subject of government control because the US government doesn't want the next generation of ASML's extreme UV lithography tools to end up in the wrong hands. So there's geopolitics at work here, commercial interests, and then actually being able to build one of these. One of these things costs close to $100 million, maybe more than that. All right, so as I tell all my graduate students, this is a wonderful time to be working in semiconductors. The Chips and Science Act, so CHIPS, creating helpful incentive for the production of semiconductors. So it's a little acronym, the Chips and Science Act, signed into law a couple of years ago, that authorized the expenditures of $50 billion to promote the manufacturing of semiconductors in the US. And so as a result of that, here's the photograph of one of the TSMC $20 billion foundries going up on the West Valley. They're building 2 of these. They actually bought enough land to have 6 of them. So if their plans work out, they'll have a $120 billion investment in the West Valley of Phoenix. Intel has been in Arizona, especially in the Phoenix area, for decades, and they're building 2 more foundries here as well. So lots of investment, in part because of this Chips and Science Act. The government recognizes the strategic importance of having semiconductor manufacturing in the US. Now, this is very good news for anybody who wants a career in this industry. Projections are very good. It's a very cyclical industry. It goes up and down, but projections are for like 600 billion, approaching $3 trillion by the end of the decade. And then this is very important. This is very recent. the Semiconductor Industry Association. So that's a trade group representing all of the manufacturing companies. They predict that the workforce will grow by 115,000 jobs by 2030. And this is a challenge because as a result of this projection, they think they could be short 65, 70,000 semiconductor engineers and technicians over the next 5 to 10 years. So there's an enormous investment going on both in training people to work in this industry and also in developing those jobs. So let's talk a little bit about the companies that are involved. Well, we've all heard about Intel, right? Intel has been very successful promoting themselves. We've heard recently about these companies that have been around for a long time but have been very successful. Taiwan Semiconductor Manufacturing Corporation, TSMC, Samsung. Global Foundries is less well known. They were the IBM chip manufacturing division until they got sold to a private equity company. Texas Instruments, I mentioned NXP. These are all here in the Valley. Some European companies, ST Semiconductors, Microchip, Micron. So there's dozens more. These are just the big well-known ones. Then of course, there are the equipment manufacturers. And here at ASU, down at our science park, we have a small division of applied materials. So they make the tools that go into the clean rooms to make the chips. I mentioned ASML. Look, this is a picture of the insides of that extreme ultraviolet lithography tool. And it looks like something out of NASA. This looks like a satellite that NASA is getting ready to load into a spacecraft. But you can see how complex something like this. Then there are companies that make a very good business selling the equipment to measure and characterize tools. So well-known ones such as Agilent, Keithley, Lam Research, and then dozens, if not hundreds of companies that provide the software and the multitude of other services that are needed. So all our engineers get jobs in all of these companies. So I'm going to wrap up in the next few minutes and take some questions, but we should just briefly touch upon graduate school. Most of you are here thinking about completing your bachelor's degree, which is great. I would call that the entry-level degree for much of this work. I'm sure Bob and Cheryl and others are going to talk to you about our 4+1 MS degree. That's a very good way to get a master's degree with just one extra year. I would say this was a very good compromise between a bachelor's degree and a PhD. For an extra year, you can get that extra qualification behind you, and it just gives you lots of opportunities that perhaps the bachelor's degree alone won't work. And then a PhD, I work with a lot of PhD students. It's very specialized. It's very good if you want to get involved in the most sophisticated, the most interesting kind of projects in industry. It's essential for academic positions. But of course, it could take 4 more years. And so you really have to love a subject to be able to spend that 4 years of extra time before you graduate with your PhD. I updated this slide recently. So 2023, this is from the Bureau. Anyways, this is a government agency that tracks jobs. And so I guess this kind of makes sense. Your average weekly income increases with the higher degree level you have, but then also the unemployment rate is lower for people who have those higher degrees. And so this is something I've seen in the industry. Depending on the cycle, they will be hiring and firing their engineers, letting them go because they don't have capacity. They rarely let go their PhD level scientists and engineers because it's taken so long to recruit those people that they just move them to another part of the company that's making money. So I think I'll finish there, Bob and Cheryl, and open it up to any questions.
Thanks very much. There was a question specifically about 439. I know Professor Kazicki teaches that, but for online students, are you familiar with how they view and see the clean room activities? If not, we can refer that to Professor Kazuki.
Yeah, no, I'm not too sure. I know he's, like I said, he's refocused that class a little bit to manufacturing, so I'm not sure how it's delivered to the online students. For my class, I have videos of this, of what happens in the clean room. So it's not the same as being hands-on in the clean room, but it's the next best thing.
Great, thanks very much. And students too, we have a lot of online students here today. I'm going to put something in the chat. Professor David Ali took students to Taiwan for a 2-week program, and we had a lot of online students go. So I know I've mentioned this in the past, but there's a news article about the program from last June, and we're going to do it again in May. So if you're curious about the industry and maybe not the history of the industry, consider that program. It's relatively affordable way. It's in Taipei for 2 weeks. It's a pretty cool thing to do if you're curious about the growth of this industry. Are there other questions, Professor Thornton, since he's here? Yeah,
Well,
we were handing
yeah,
a lot of them over the chat while you were talking, so they're
okay.
mostly just questions about specific classes and
Well, very good. Like I mentioned, this is a great time to be working semiconductors, and you can find my email on the ECE website. So if you think of anything, send me an email and I'll get back to you.
Well, thanks very much for being here, Professor Thornton. We appreciate your time, and thanks for talking about this
Very
cool,
good. Very
exciting
good.
area. Well, I do
All
have
right.
one quick question that should be answered if you have 1 minute. So,
Sure.
some students who are curious about taking more courses out of our circuits area versus this area, they're
Yes.
very related. Do you have any comments on if someone wanted to work like in the semiconductor industry, um, what are the specific differences
Yes.
between these and
Yeah.
those courses?
Yeah. So it's very interesting. So digital electronics is so complex that you can you can become a VLSI engineer without really knowing how the transistors operate. Because if 10 billion transistors, you're not concerned with each individual transistor. I think the real opportunities there are in the analog RF area. So there's a shortage of people who understand how RF integrated circuits work, and being able to build them in these state-of-the-art CMOS foundries requires a very good understanding about the compromises between a device that's designed for analog and one that operates designed for digital applications and operates in an analog regime. So I think I always tell my students to get some understanding of how RF integrated circuits work. So that would be my answer there.
Yeah, thanks very much. And of course, you students, you'll specialize more in these things at the master's and higher levels, but this idea is to get you a pathway into it. So
Yes.
thanks again for your time, and we really appreciate it.
Very good. All right, everybody. Enjoy the rest of your day.
Great,
Thanks
and it
again.
looks yeah, and it looks like our next presenter is here. So we're going to move on to the power area in just a moment here, and that presenter is Professor Mike Randrum. So thanks for being here, Professor Randrum.
My pleasure. You can hear me okay?
Yes,
I can hear you great. Yeah.
Great.
thank you.
And Mike or Professor Randrum will probably recommend the students add questions to the chat, and you can either check those out at the end, or if you want me to facilitate those, just let me know.
Sure, I'd probably check them out at the end.
Great.
Okay, thanks all for being here. I'm going to talk about the Electric Power and Energy Systems program. Electrical engineering is a very interconnected set of discipline to study, so it doesn't really have one meaning. And Professor Thornton talked about power in his presentation. You're going to hear about power in this presentation, but it's all related, right? You can be someone who takes those courses and these courses and develop specializations that are unique and beneficial. And so although we kind of silo ourselves into these areas, it's really for your benefit, in my opinion, to give you an idea of the different areas you can study, but you don't necessarily have to feel strongly committed to one area or the other. For example, we have lots of power students take courses about solar energy because it's relevant for that renewable resource, but they're in the power area. Similarly, I do circuits. I'm a power electronics person. I'll talk about that. And I teach students that study the grid at a very high level. So I wanted to open with that. You're ultimately getting an EE degree, and that can mean a lot of things, in my opinion. So in the Electric Power and Energy Systems program at ASU, we have one of the largest programs. So actually, I did my PhD at MIT, and at MIT, you can't even take one power systems program. They don't have that offering at least when I was at MIT. And ASU is unique in that it's very committed to power. One of the reasons I wanted to come here, and one of the reasons so many have thrived in our program, is because there's this real commitment to power. Power is a useful thing to study because it's hard to outsource power. That's what they always told us, and it's true. Right? You can't take a transmission line and ship it overseas. The people who operate the power system here, the people who operate the power plants here, they have to be US based. And technologies that can better leverage electricity, like what I do in power electronics, there's huge markets for them in the US. So there's lots of opportunities for someone in power to be employed in power. ASU is among the top as regards power in particular, as I mentioned, and there's excellent employment opportunities. This is the group of power area faculty members that you could interface with at ASU. I leave the names up, so if you want to go take a look online, you can. Just at a high level, we have sort of people that study the power system and the energy that goes in that system, the movement of energy through that system, and the utilization of that energy. And so all of these different faculty specialize in some subsection of those three ideas, and all carry out fantastic research that most of them would be very happy for you to be involved in if you reach out, including me. So what are we about? If you take a power course with me, I always start my courses with this slide, which shows how the US uses its energy on a yearly basis. And so at Livermore National Labs, every year they'll cobble together this chart, which is actually a very difficult thing to estimate. What it tells us is all the ways we are assumed to be generating or estimated to be generating energy. So the primary resources, so we have petroleum, biomass, just burning stuff, coal, burning stuff, natural gas, burning a different kind of stuff. And then up here we have emissions-free resources, wind, hydro, nuclear, and solar, meaning they don't emit carbon dioxide. They estimate what percentage or what proportion of our energy usage came from these primary sources, and then also tell us an estimate of how that energy was used. And the biggest way that we use energy in the US is for generating electricity. So most of the energy we burn, the biggest proportion of it, is going directly into producing electricity, which we then go and do other useful things with. And so our concentration, EPES, is about this, right? It's about how did we generate this electricity? Let me turn my, how did we generate this electricity? What's the infrastructure that allows us to take that generated electrical power and move it to somewhere useful? And then what are the broad approaches we have for utilizing that electrical energy? And that's a very broad question, right? Because in principle, every electrical thing relies on some source of electrical power. And what I study, power electronics, is focused on making systems that can utilize that electrical energy in the most efficient, smallest, best way. But again, for that reason, I stress how broad this area is and how you can get a really nice electrical engineering base by focusing on this area. In particular, so this just shows us every year. So this is the latest data that's available from Livermore. It was published in 2022. The 2023 data should be out soon. And we see, okay, it looks like most of what we're doing is burning stuff, right? We're burning gas to run cars. We're burning gas to generate electricity. And this that many of us are excited about, which is emissions-free or renewable, these resources are still a pretty small proportion. So you wondered, like, why are people getting so excited about this? And the reason is, if I started tracking percentage total US electricity generation over time, we would see some very nice, encouraging things. So if we had this presentation 10 years ago, we would see that by far and away the way we generated electricity was by burning coal. And over time, coal went down. What replaced it was actually mostly natural gas, but not entirely. Something else stepped up to fill up this gap. And the things that are stepping up are renewables. So even though wind, which is blue here, and solar, which is orange here, are relatively low in proportion to the other main resources, if we dialed into just those resources, we would see something very encouraging, which is this. it looks a little linear, but it's exponential, especially for solar. This is exponentially growing year by year. And integrating these resources into our system is a fundamentally different way of operating the system than what has been done in the past. And so even though power may seem like this old antiquated area, right? Back in the day, if you were an electrical engineer, it meant you studied machines, generating power, power plants, and moving power by electrical lines. That is what an electrical engineer was. The thing is, today we still learn those principles, but now things are fundamentally changing. And so we need young, bright, encouraging minds to be studying these hard problems to help us transition from a world as it existed 100 years ago to the world as it's going to exist 50 years from now. So that's speaking very broadly, right? We talk about all the power, all the sources of energy we have, and then we broadly say we generate electricity and then we use it in all these different very broad sectors. But these principles that you learn at this very broad level extend to like more contained systems. So things like aircraft and ships, you can think of them as contained power plants, power distribution systems, and power utilization systems. So learning the principles of EPES, electric power and energy systems, doesn't just confine you to having to be a grid person. You can be someone who becomes an expert in any system that has some electrical subsystem that operates it. The principles you learn at the big scale extend to the small scale. Okay, so that's the broadest motivation. We're in the business of how do we generate electricity? How do we move it? What do we do with it? And we take those ideas and we partition them into these different concepts. So I can generate power, I can transmit and distribute. So transmission and distribution, that means transmission means take it from some central plant and send it far away to where people are. And distribution means now that it's close to the people, how do I actually get it to the people? And those are fundamentally different problems that require very different thinking to solve them well. Finally, once that electricity has gotten to the person that wants to use it, how do they use it? How do I turn whatever voltage and power level is coming in on their power lines into something useful for them to do useful work with? And so we offer courses in all of these three different areas, and we have research going on in all these different areas. So power generation, right, that means how do power plants work? What are the sources of renewable resources? How do we extract energy from those renewables? What does it mean for those renewables to be distributed rather than centrally located? And also markets, right? What is it? Why do we buy energy at the cost we do? And how do we decide what energy is worth? Transmission distribution is a huge segment in a classic power systems area, which is how does the grid work, right? How do you model the grid? When something fails in the grid, how does it recover itself? How do you prevent failures from propagating in the grid? If you want to add more power to the system, be it generation or consumption, how can you do that in a structured way that isn't going to throw the whole grid? This is the kind of thing that's incredibly important, but sort of in the background, right? You don't think about the electricity until it doesn't work, right? It's when your house has a blackout that you want to get EPES or SRP on the phone. Up until that point, it's just in the background. So it's very fundamental to how we live, but you know, not something we concern ourselves with until something goes wrong. It's very, very important. And finally, utilizing electricity. I would say this is extremely broad. I would argue that every other pathway that you can take, every other specialization that we offer at ASU, fundamentally is about how you utilize electricity. We're specifically interested in making the best systems to support those other systems. So how can we give the high frequency radars that Professor Thornton was talking about, how do we give them the cleanest power we can in with the smallest form factor of conversion that we can? So that's broadly speaking what we worry about, in addition to things like electric machines. So for an electric car to run, it has to have wheels that spin. How does an electrical system make wheels spin? That's something you get to learn about in the specialization as well. So here are our actual courses. I'll go through them each step by step, but they're sort of nicely partitioned into how do you generate electricity? Sorry, these two, generate electricity. How do you transmit, distribute that electricity? And then what are the key ways that we use that electricity. And at the top here is our 360 course, which is a pathway course, which is essentially going to be a crash course in all of these different areas with a lot more breadth than any of these single courses, but less depth. So it's a great way to get introduced to these ideas, see if you like the concepts, and then go from there and study any of these or all of these different areas in depth. We also are a strong supporter of the senior design program. It's something I've definitely engaged with. And so you can definitely use your senior design project as a way to meet your EPES specialization requirements. All of these courses are offered online except for 473. This is a course I teach that I just restarted a couple of years ago. And we're hoping to get that online sometime in the next few years. But unfortunately, right now, it's only in person. So this is the actual requirements. If you want to specialize in this sub area, you got to take our pathway course and then 9 hours of technical electives in the power and energy area. So that's the electives I just showed, as well as some other combinations. You can talk with your undergraduate advisor if you're interested in pursuing that. So what are these courses about? Electrical power plants is very nicely named about the plants where we generate power. So you learn all kinds of things. And it's kind of a remarkable thing. Cavemen lit fires to generate heat to warm themselves up. We, at the scale that we generate electricity, we do fundamentally the same thing, more or less. We light something on fire to generate heat, to boil water, to make steam, to somehow make electricity. And that process is a very interesting one. There's a lot of engineering that happens in there and a lot of ways we can improve those systems. And this is a core idea that 463 covers. How do we turn these primary sources? How do you turn a lump of coal? How do you turn a gas? How do you turn the sun? How do you turn a rotating blade into electricity? 460 specifically focuses on nuclear power engineering. And I highlight this in part because very unique at the undergraduate level that you will get this kind of specialization in nuclear power engineering. Keith Holbert, one of our faculty, is an expert at this and a real champion of this part of our curriculum. And you can even get a certification in nuclear, in nuclear studies from ASU, which I think the undergraduate advisors can tell you more about. I certainly know students that have done it. And it's a remarkable thing to have an education on before you get to your graduate studies. I didn't really learn how a nuclear power plant worked until I did my PhD. And I took a course because I was interested. Well, and this is a kind of a key idea throughout. One of the reasons I love power engineering, and again, I'm a power electronics person, so I sort of sit between circuits and power. But in general, I do think this is true. We've found, talking to students, that the reason they like this stuff is because it is very applied. Right? You learn about some abstract mathematical concept that allows you to describe how power flows in a system, but then you realize that that abstract mathematical constant is sort of fundamental to the reason why you have lights working. And when something goes out, a blackout happens, you can understand that system, what happened through this tool that you learned. And so this connection between this abstract tool that otherwise seems just like an equation or some simple model turns into something very useful and allows you to really engineer the world. Power engineering is very hands-on in that respect. I think that it strongly rewards you for developing your engineering toolbox. If you want to be a power electronics person, like students that I work with are, you've got to know circuits, signals, electromagnetism, controls, physics, mathematics, and statistics, including machine learning, and how to code, or generally how a computer works. The more you know about any of these subjects, the better you become as a power engineer. And I think that's a very rewarding feature of studying power. One of the reasons I chose to study it and why I specialize in it. Theory becomes practice. In our transmission and distribution side, we have 470 and 471, which is basically what are the devices that comprise the grid. So what fundamentally makes the grid work are relays, current and voltage sensing, transformers, protection on all those systems. You learn about that in 470. 471, this is our classic power systems course. Professor Vital, who teaches this course, wrote the textbook that I used when I learned this stuff years ago, right? So he's a real legend in this area, and being able to learn from him, I think, is specifically a real treat. Though I think all of our faculty are fantastic. In this course, you'll learn how to study the electric grid. How do I take this big, complicated network of generation and transmission and utilization, and how do I combine it into something I can actually understand, study, and then hand off to the power plant and say, or the power operator, and say, you can use this model to make sure everybody has power. And you can use this model to understand the impact of something that may compromise people having power. You get a lot of capability from that one course. And taking both these together is a fantastic baseline for becoming an expert in transmission and distribution. It's a good time to also mention that we have very strong ties to the local utilities if you're in the Phoenix area, or in the Arizona area, I suppose. Salt River Project and Arizona Power Systems. We routinely have students doing internships with those companies and then getting employed by them. And again, it may seem like old stuff because the grid is ancient, right? The grid has been around for as long as, definitely, I mean, 100 years plus, right? But the reality is it is changing in very interesting ways. And so there's a lot of active research in this and a lot of need to have people that are up to know on what's changing, right? We're going from big monolithic power plants out of sight that produce a lot of power and then get shipped to you into resources that are distributed, collecting energy wherever you want, and maybe utilizing it close, maybe giving it to your neighbor, maybe shipping it off somewhere very far away. And understanding that is fundamentally different. Building that well is fundamentally different than what we've been doing. You'll hear the word inverter-based resources a lot. That's power electronics. So we're electrifying much of our loads. So back in the day, when you might have just plugged in, say, a hairdryer or a vacuum cleaner into the wall socket in your house, that was just plugging a motor into the wall. Today, it's ubiquitous that instead there'll be a circuit between those systems that is processing in a smart way the energy flow that happens. That gives you lots of efficiency and control benefits, but it comes at cost and size detriments, which is something that power electronics people study. And inverter-based resources are those resources that only work because you have power electronics to make them work. Keeping in mind now it's a smart thing, so this is a thing that's really emerging, is I had control, I had efficiency, I introduce complexity, but I can manage it because I'm a smart engineer. But then I also create possibilities for cyber insecurities, right? The worst thing that could happen is an attacker gets hold of the systems that run the grid. And so there's a lot of investment and interest now, and we have faculty working hard on these problems. But how do you make the grid cyber secure? That's something that's seen a lot of investment as well, and something you will encounter studying electric power and energy system. Then we have the final thrust, which is electric energy utilization. This is my sub area of expertise. I teach both of these courses as well as 360 and a new graduate course on power electronics I just introduced. And so power electronics and power management is fundamentally about these circuits that process energy. So before you take such a course, most of the circuits that you're going to study are signaling circuits. So when you learn about a Bode plot, for example, you think about filtering. You think that there's a signal that's coming in. I want to filter that signal, something different. Or if I'm thinking about a MOSFET or a BJT, a transistor, I think of it as an amplifier. How do I get a small signal into a larger signal? Those circuits are, broadly speaking, about information. How do I send information from one port to another with as much fidelity as possible? Power electronics is a fundamentally different way of thinking about a circuit. And so as power electronics people, we concern ourselves with, how do I transport energy from one port to another with the most efficiency? So instead of information, I concern myself with energy. Instead of fidelity or quality of information, I concern myself with doing that energy exchange while losing the least amount of it. And this is just a very, very popular area. They forecast that 80% of the energy we use by 2030, so in 6 years, is going to pass through a power converter, a power electronic converter. And so this is a great space to be in. Lots of people are hiring. You want to make electric vehicles work or solar panels work, wind turbines work, you have to have power converters. So it's a great way to, I think this is in particular a good way if you're more interested in the circuit side, taking a power electronics course is a great way to round out that expertise. Then electrical machinery is a course we just restarted. So this has always been popular because that's how you generate electricity. Earlier when I said, how do you take burning stuff and make electricity? The answer is you make a fire, you boil water, you create steam, you push that steam through a turbine, that turbine spins, and you can take spinning blades and relatively straightforwardly make electricity through what's called an electric machine. And so it's a very important thing to know to understand how we generate electricity, but also what if you've ever been in a Tesla and you just tap the accelerator and suddenly you slam back into your chair, why is that? That's because an electric motor has a very high torque response. Why? You learn those things in electrical machinery. And I think that's starting to get more and more popular because there is such an interest in electrified vehicles. And any electrified vehicle depends on a power converter to run things, an electric machine to drive you forward. And this is my spiel for power electronics. You would be hard pressed to think of an application today that doesn't rely on a power converter to operate. So all of these systems, or any system that you can imagine, there is a very high likelihood that that energy that's being processed in that system is passing through a power converter. And so if you want to, it's a great way to get plugged into all these different applications, which again isn't surprising because if you're in electrical engineering, right, the heart of everything you do, say you do go and study radio frequency radar, that RF radar's got to be powered by something. And so you can be a power electronics person studying high performance aircraft, battery energy storage systems, or you could be someone that makes like chargers, like cell phone chargers, like these things, right? You build these too. And so I love power electronics, and I'm going to stop harping on it to not show bias toward my own sub area. I think all these areas are great and worth your time. We're active in the in the senior design project space. So as part of your specialization, you can take credits with your capstone. And here are some example projects that have been in support of that for our senior students. You can take a look at this afterward. We're very active in research. As I said, you saw we have a number of faculty specifically in power. Our department is actually called ECEE, Electrical, Computer, and Energy Engineering, which is very unique. Most places are just an electrical engineering program. And I think that really emphasizes the commitment of our faculty and our department to the concepts of energy. And so there's PCIRC, which is a very well-regarded power systems consortium headquartered at ASU that involves 40 plus companies, faculty from all over the country that do cutting edge research. Every year they issue projects and do cutting edge research and connect the research we're doing here to real world applications in industry. A fantastic way to get connected to the broader power systems programs in the country and in potential employers. And we also have this electric vehicle center, EVSTS, which is a consortium of a number of universities, and they're looking at ways to, they're engaging with companies to do specifically electric vehicle research. We've got lots of nice laboratories. Again, here's our power electronics one. We have lots of capability. We can basically do every kind of power conversion you can imagine, from like 10 kV, multiple hundreds of kilowatts, down to 50 watts or lower at tens of volts. And so this is our wonderful research space. This is really for our researchers, but we do, especially, I'm very engaged with the Fury and Surrey programs. So if you're interested in doing undergraduate research, our power faculty would love to talk to you. And in particular, you can feel free to reach out to me if you have interest. Down here is an example of one of the cutting edge power converters my group makes. This thing processes 1,000 watts and is about the size of a couple pennies. It's this thing here. So really cool stuff, real hardware. It isn't just abstractions when you get into power engineering. We also have a number of power systems lab. We just had one introduced that it's beautiful. You should come see it. It's on ERC 5th floor. It's this lovely, it's a mimic of what a power system control station looks like. So we've got this big screen that would monitor all the different parts of the grid. Then you have all the operators sitting there with their two screens and their sub information. And I understand that's going to be integrated into future courses, which is very exciting. And the takeaway message is we have a lot of great facilities that many universities don't have because there is such a commitment to energy at ASU. Here's some other great examples. We have the lab for synchrophaser technology. This is Professor Anna Mitra-Pal's lab, where they study, one of the many things they study is how do I develop and understand the sensors that go into the grid, very distributed, to tell me what the grid is doing. And we also have the lab for machine learning and power systems. This is led by Professor Yang Wang, and he's a machine learning expert, and he sees a lot of opportunity in leveraging big data machine learning concepts into the grid, which is a big data, highly distributed system that is very unwieldy. So if you model it better, if you make better predictions about how to control it, overall, you make a better system. So lots of things to study in this area. I think it's a great area to choose. It's certainly the area I chose to study, and happy to take any questions if there are any. Thanks for your time.
Thanks, Professor Randrum. That was fantastic. A special thanks for connecting it to real specific industry things, and the charts you shared early on were super interesting. The couple of questions that came up were, some of them are advising related. So any students, if you're in the electrical engineering BSE and you're curious about the power concentration of this same degree, I put a link in the chat where you can get basic information, and you should definitely speak to your academic advisor about the differences in it. It's not that difficult to have the different degree, really. It's just same amount of courses, it's just the different choices that you make. I also added to the chat, since Professor Vitale was mentioned, he's a honored and respected faculty member, and he's often cited, as all our faculty are, but he often gets cited for his background. So I put a recent article that he was interviewed for.
Great.
This is a good one. Do you see this question about Fury, Professor Randrum?
Sure. Let me check it out here. The best way to get involved in Fury, there's a couple ways. It depends on what level of your education you're at. In your first 2 years, your job is to get as many A's as you can, meaning learn the fundamentals. And if you ever need a push, just remember that the fundamentals are useful, because if you don't know your fundamentals, you can't do all this cool stuff that we do. And so you learn your fundamentals. I think after second year is a great time to start reaching out to faculty. So that can be, you can reach out to me if you're interested, but just cold emailing faculty. Faculty are generally interested in engaged undergraduates. But if you do take, for example, our pathway courses, talking to your pathway professor is also a great way to get connected. If they see that you're interested, I've had this happen, and they're not directly interested in my research, I can connect them to another faculty. So I think my general answer would be, don't be afraid to ask. And most faculty will be interested in you seeing that opportunity through. Fury has deadlines in the middle of every semester. You need to have a faculty advisor you're working with. So you want to reach out to them early to brainstorm ways you can work together. And generally, they'll have an idea of how you can be useful and get some good research experience, including if you want to reach out to me, I'd be happy to talk to you.
Yeah, I'll second that. Professor Randrum, I appreciate you being here, and especially your excitement. He's definitely interested in talking to students and getting them as excited as he is. So we appreciate this awesome energy you give to the students.
Sure, happy. It's so exciting. I want to leave with, engineering is hard, but it's for good reason, because you learn how to do stuff other people can't do, and you become as close to a magician as you can, and they pay you for it. So it's worth your time. It's worth the struggle. We all have to go through it. It's going to be worth your time. Best of luck to all of you.
Yeah, well, thanks again for your time, and thanks for your questions, students. And we really appreciate being here, and we'll see some of you next week. Thanks again, Professor Randrum. We really appreciate it.
Yes,
Take care.
thank you
My
so
pleasure.
much.
My pleasure.